Today we are going to learn about scaling transformers beyond 100K tokens. We will explore strategies to extend transformer models' context limits and enhance model performance in real-world applications. Welcome to our deep dive into scaling transformers beyond 100K tokens. In this video, we'll explore the challenges and strategies for extending the context limits of transformer models. Understanding these techniques is crucial for processing large datasets effectively. By the end of this video, you'll know practical methods to enhance model performance in real-world applications. Transformers have revolutionized the field of natural language processing with their ability to handle long sequences of data. However, they are inherently limited by the context length they can process at once. Typically, transformers like BERT or GPT handle around 512 to 1024 tokens efficiently. So, what exactly is a context limit? In simple terms, it's the maximum number of tokens a transformer can process in a single pass. This limitation arises due to the quadratic time complexity associated with the attention mechanism, which makes it computationally expensive to handle longer sequences. The context length impacts the model's ability to comprehend and generate coherent text, especially in tasks requiring long-range dependencies. Extending this limit allows transformers to process more context, leading to more nuanced and informative outputs. However, achieving this requires innovative approaches to manage computational resources effectively while maintaining or improving model accuracy. Scaling transformers to handle more than 100K tokens presents several challenges. First, there are increased computational requirements, as the attention mechanism's complexity grows with the length of the input sequence. This leads to significant memory management issues, as storing the attention weights for such large contexts can exceed the capacity of standard hardware setups. Furthermore, there's a delicate balance between maintaining accuracy and ensuring efficient performance. Larger context windows can introduce noise and irrelevant information, potentially degrading model performance if not handled correctly. Hardware limitations also come into play, as even high-end GPUs struggle with the memory and computational demands of processing such extensive sequences. Additionally, algorithmic challenges arise in efficiently splitting and managing data to ensure the model can still capture long-range dependencies without overwhelming the system. Addressing these challenges requires a combination of hardware innovations, algorithmic optimizations, and novel architectural designs. Current transformer architectures, such as BERT and GPT, have set the standard for performance in various NLP tasks. These models use a multi-layered attention mechanism to process input sequences, allowing them to capture complex patterns and dependencies. However, the standard architecture is limited by its maximum context length, which typically ranges from 512 to 1024 tokens. This limitation is due to the quadratic complexity of the self-attention mechanism, which becomes computationally expensive as the sequence length increases. While architectures like XLNet and T5 have introduced improvements in handling longer sequences and capturing dependencies, they still face constraints when scaling beyond 100K tokens. Comparing these architectures reveals that while they differ in implementation details, they share common bottlenecks in context handling. Despite these limitations, there is significant potential for scaling improvements through architectural innovations, such as sparse attention mechanisms and memory-efficient processing techniques, which we'll explore in later sections.
To extend the context length of transformers, several innovative techniques are employed. One such approach is the use of sparse attention mechanisms, which reduce the computational burden by focusing only on relevant parts of the input sequence, rather than processing the entire sequence at once. This can significantly lower memory usage and increase processing speed. Memory-augmented networks, such as those using external memory modules, allow models to store and retrieve information over longer sequences without being constrained by the fixed context window. Hierarchical attention models introduce a layered approach to attention, enabling the model to first process smaller chunks of the sequence, and then integrate these into a broader context understanding. Chunking and recurrence strategies involve breaking down the input sequence into manageable parts and processing them iteratively, while maintaining a memory of previous computations to capture long-range dependencies. These innovations in architecture design are crucial for extending the capabilities of transformers to handle over 100K tokens effectively, paving the way for more advanced applications. Effective memory management is critical in scaling transformers to handle larger context lengths. Efficient memory allocation strategies ensure that memory resources are optimally used, preventing bottlenecks that could slow down processing. Memory-efficient algorithms, such as those involving sparse attention or memory compression techniques, are essential for reducing the memory footprint of large models. Dynamic memory management techniques adapt to the changing requirements of the model during inference, allowing for more flexible use of resources. However, there are trade-offs between speed and memory usage, as optimizing for one can often come at the cost of the other. Balancing these trade-offs is key to maintaining model performance. Additionally, hardware optimizations, such as using specialized processing units or leveraging distributed computing resources, can further enhance memory management. These strategies are integral to the successful scaling of transformers and are a focus of ongoing research and development in the field. When scaling transformers to handle larger contexts, performance trade-offs are inevitable. One of the primary challenges is balancing accuracy and efficiency. While larger contexts can provide more information, they can also introduce noise, which may affect the model's ability to make accurate predictions. It's crucial to perform a cost-benefit analysis to determine whether the benefits of increased context length outweigh the computational and memory costs involved. This analysis is especially important in real-world applications, where resources are often limited and efficiency is paramount. Considerations for specific use cases, such as language translation or document summarization, also influence performance optimization strategies. For instance, strategies that work well for short text classification might not be suitable for long-form text generation. As such, developing a nuanced understanding of these trade-offs and considerations is vital for optimizing transformer performance in practical settings.
The ability to scale transformers to handle over 100K tokens unlocks a plethora of real-world applications. In industries like finance and healthcare, where large datasets are the norm, extended context capabilities allow for more comprehensive data analysis and decision-making. For example, in financial markets, transformers can analyze vast amounts of textual data, such as news articles and financial reports, to identify trends and make informed predictions. In healthcare, the ability to process long medical records enables more accurate patient diagnostics and personalized treatment plans. Several case studies highlight the successful implementation of these extended context capabilities. One notable example is the use of transformers in legal document analysis, where the model's ability to process entire contracts or case files in context leads to better information retrieval and analysis. The benefits of extended context use are evident in these scenarios, as they result in more accurate and insightful outcomes. However, these applications also provide valuable lessons on the challenges of implementing such systems, emphasizing the importance of balancing scalability with practical considerations.
As we look to the future, several trends in transformer scaling are emerging. Research continues to push the boundaries of what's possible with these models, seeking to overcome current limitations and unlock new capabilities. Potential breakthroughs in context scaling may come from advancements in AI algorithms and hardware, such as the development of even more efficient attention mechanisms or the use of quantum computing to handle complex computations. The role of AI in future transformer development cannot be understated, as it will likely drive innovations in architecture design and optimization techniques. The impact of transformer scaling on the evolution of AI is profound, as it enables more sophisticated models that can tackle increasingly complex tasks. Predictions for the next decade suggest that transformers will become even more integral to AI applications, with the potential to revolutionize fields like natural language processing, computer vision, and beyond. Staying informed about these trends is crucial for anyone involved in AI and machine learning, as they hold the key to the next generation of intelligent systems. In conclusion, scaling transformers beyond 100K tokens is a challenging but rewarding endeavor. We've explored various strategies for extending context limits, from innovative attention mechanisms to efficient memory management techniques. These advancements are crucial for processing large datasets and improving model performance in real-world applications. While challenges remain, including balancing accuracy with computational demands, the future of transformer research is promising. We encourage you to delve deeper into this exciting field, as continued exploration and innovation will undoubtedly lead to groundbreaking developments in AI and machine learning.